origami and mathematics. Modular polyhedral origami and mathematics. To start, I'm going to pass out, and they are pretty sturdy, but probably if you throw them on the ground and stomp on them, they're going to break. But I'm going to pass around these origami, and I'll be describing what they are through the presentation. So just pass them around, take a look, touch them, feel them. So, overview. We're going to discuss my goal of this project, my rationale behind this project, the polyhedra I chose, the golden ratio, the mathematical concept of phi, the Fibonacci sequence, the 3 golden rectangles that help determine the shapes, pictures of the assembly of the polyhedra, the challenges I encountered, the lessons that I learned, the results, the acknowledgments, and the references. Slide. So this is my goal. I desire to explore modular origami, the various units involved, and the mathematics of polyhedra folding. It's a rather simple, however, pretty big idea. Slide. So I started this project because I had a passion for origami. When I was about 7 years old, my cousin came to my house, and he taught me how to fold a simple origami swan. And ever since then, I've thought it was so interesting what you can make out of a flat piece of paper. And that's taken me from different types of origami into this type of origami, into different interests, and it's an interesting process. So I had a passion for mathematics. I think it's really interesting the way math can describe things, and I wanted to see how it could describe the shapes that I was folding, that I wanted to fold. I wanted to explore something in detail, starting out from the beginning with this concept of capstone presentations. I knew I wanted to do something fully and all-encompassing for that topic, and I decided that this would be an interesting potential topic to pursue. I'm not a very artistic person, so I wanted to do something that would allow me to express myself through some artistic means, and I think that I achieved that through these shapes. They're not only visually appealing, but you can touch. They're kind of they have this appeal that makes you just want to reach out and feel the edges, and that's kind of what I was aiming for. And it was a general curiosity because I had done origami before, but never on this scale, and never this type of origami on this scale. Next slide. So we're going to be exploring 2 shapes, and initially I intended, and we'll discuss this later about my initial intentions through this project. I intended to explore polyhedra in general. But we're going to focus on these 2 shapes, the polyhedra, the icosahedron and dodecahedron. So in polyhedron comes from the Greek for many, and hedron comes from the Proto-Indo-European for side. So effectively, polyhedra or polyhedrons are many-sided 3D shapes. And this is a neck for the icosahedron, this is a neck for the dodecahedron. Just so you can see what it would be laid out if it was kind of just a flat piece of paper that you folded it up on top of itself. Next slide. So this is the golden ratio. The golden ratio is expressed geometrically in terms of a line segment, is best represented as this right here. So basically all this means is A plus B is to A is to B, which is to say that this length to this whole length is the same as this length to this length. And to achieve that proportion, it's a rather specific idea, it's a rather specific number. Next slide. Phi. Phi is about 1.618, and this proportion allows you to achieve a lot of really cool proportions in the real world and mathematically. Next slide. And a couple of ways to get phi are 1 plus 1 over 1 plus 1 over 1 plus 1 over, and you eventually get 1.618, and 1 plus the square root of 1 plus the square root, and all these different ways. And again, a visual here that helps represent exactly how you get 1.618 out of these proportions. Next slide. So the golden ratio can be represented by the ratio between any 2 successive numbers of the Fibonacci sequence. The Fibonacci sequence is basically a series of numbers in which each successive number is the sum of the previous 2 numbers. What that means is that starting from 0, you get 0, 1, 1, 2, 3, 5, 8, 13, and so on. And as represented in Pascal's triangle, which basically the top number is the bottom number is the sum of the top 2 numbers, you end up with 1 and 1 make 2, 1 and 2 make 3, 1 and 3 make 4, 1 and 4 make 5, 1 and 5 make 6. And you can see that it ends up, if you do these diagonal lines, you end up seeing the Fibonacci sequence in that pattern. Next slide. So the Fibonacci sequence can be seen in a lot of cool different things. One of the interesting things about the Fibonacci sequence is the Fibonacci spiral, which is basically it's proportionally a part of a rectangle that has this, that is a golden rectangle, which means that one side is 1, the other side is phi. And if you see here, that what I actually realized was that well, if you form a square inside of the golden rectangle, then another rectangle is formed by the golden rectangle, and that keeps happening infinitely. And these are a couple of ways of representing the golden spiral through an aloe vera plant, a pine cone, sunflower, and a nautilus shell. And you can see it in nature, which is rather interesting, that this mathematical concept of the golden spiral isn't just on a piece of paper. Next slide. So the 3 golden rectangles are basically, if you take a golden rectangle which has these side lengths of 1 and phi, you end up, and you put them all together at 90-degree angles, you end up with this shape here. And if you take these points, you form the dodecahedron's faces, and if you take those points, you find the vertices, the points of the icosahedron, which is rather interesting that you can derive these 2 shapes from this one weird combination of the value of phi. And here's another golden rectangle, just for emphasis onto that combination of golden rectangles. Next slide. And an easy way to visualize this, which you could probably see if you take this one, and you try to put this one inside this one, you can see that the points of the icosahedron form the faces of the dodecahedron, which is to say that the 12 vertices or points of the icosahedron follow the 12 pentagonal faces of the dodecahedron. Next slide. So now we're going to get into the pictures. I folded four shapes for polyhedrons or polyhedra. And the first one that we're going to be talking about is the lesser stellated Shinobi origami icosahedron. A mouthful, but all it basically means is that it's a 20-sided shape that is pointed. So it's basically it's this shape in which each triangular face forms a triangular point. That's all that this thing is. What's interesting about it is that what's interesting about the icosahedron is that each face is an equilateral triangle. Unlike this stellated icosahedron, this is the greater stellated icosahedron, which we'll talk about in a minute, each face is an isosceles triangle. Next slide. It took 30 Shinobi units to fold, which basically, and the Shinobi unit is a common shape. All modular origami is formed of modules, that's why it's called that. And modules are just units that comprise the shapes. All shapes are formed through these units, and all these units basically work through a latching system. This latching system is comprised of a pocket and a flap. You can see the pocket here where that blue strip is, and you can see the flap there, and they all interconnect. So as you can see here, it took 30 of these units, which took about 5 hours to fold in total. You can see in this slide the process of putting it together. We'll go through it like 2 or 3 times. Just watch. Next slide. This is the penultimate unit, origami dodecahedron frame. What I really liked about this shape was that you end up with these other pentagons inside pentagons, which was kind of unexpected when I initially found the module online. Because a lot of the time you'll Google modular origami, and you'll see directions for a simple unit, but they don't always show the finished model, what you're going to end up making. So it can sometimes come as a surprise what you're actually doing. Next slide. What I did here was I laid out all 30 units, and then I put 3 together, and you could, just so you could see that there would be 2 rows of 5. This is also an animated GIF image of the assembly. Next one. This is the triangle edge module icosahedron. Again, the icosahedron has 20 faces and 12 vertices or points. The triangle edge module is called that because it basically forms equilateral triangles. But what's cool about it is that each triangle is comprised of 3 units Each triangle on these is comprised of 3 units, and each piece is one of the 2 edges of the unit. And if in the next slide, you can see that side's 1 edge, that side's 1 edge, and it takes 30 of these. And that was wound up being a pattern that I noticed in folding these 4, that it just so happened, this doesn't always happen with modular origami, but it just so happened that I wound up folding, all models took 30 units to fold, all of the 4 that I chose. And this is an animated GIF image of the assembly. The assembly alone takes about half an hour. So, because, especially on this one, because it's really hard to get these flat faces perfect, because you end up having to reach inside and then latch within the actual shape towards the end. Next slide. This is the greater stellated tornillo modular icosahedron. This is a lesser stellated icosahedron, which just means that the points are more shallow, they're not as high, they're not as long. And this is a greater stellated icosahedron. So there are still 20 faces, however, each face forms a point. Next slide. It also took 30 units. You can see all of the units laid out here before folding. Next slide. This was the assembly. To assemble it, I initially did a point, and another point. So it took 5 points to complete. You can see the 5 points right here, 1, 2, 3, 4, and 5. Next slide. So challenges. In terms of time management, I had a real need for planning, because when I initially started, I didn't have a clear plan. I didn't have a clear plan of how much time I was going to fold. Really, I didn't even know what I was going to be folding. It started out with an interest in modular origami, and I narrowed it down to polyhedra, and I narrowed it down to 2 specific polyhedra, the icosahedron and the dodecahedron. So planning was really important there, to know what you're doing and then actually do it. So acquiring my materials was a little bit of an issue. With help from my parents, I was able to buy online some Japanese origami paper. The research was a bit of an issue, because I had to do a lot of looking online to find specifically these shapes, because I had decided these are the shapes I'm going to make. And then I had to find modules that you could use to make those shapes. And when usually it's the modules themselves, not the models that are created from them online, you end up having to experiment a bit and see where you're going to go with it. So there were a lot of different ones to look at, and the variety was a bit overwhelming. So, and then researching the math, because there's a lot of mathematics literature on polyhedra, and really where they come from, and how you can form them using different methods. And I wanted to make sure that I described enough to appeal to an audience, but I wanted to also make sure that it was simple enough for people to understand. Next slide. I realized early on that planning was a big issue, as I previously mentioned. I had to lay out my time beforehand. I would sit down, and this is something that I tend to do with work in general. I spent a long period of time in big bursts rather than sectioning it out. So I spent like 5 hours on each of these, just sitting down, folding units, putting them together. I need to stick to the schedule. If I was going to have a schedule, why not stick to it? So it was a rather difficult thing to have this knowledge that I was going to be sitting down for hours and hours working on these beforehand, and then actually going to do it, because then I would be kind of, even though it wasn't hard to do, I would kind of not look forward to that kind of tedium. And don't do something you don't fully understand. The reason I bring that up is because this specific shape I initially thought was going to be a stellated dodecahedron, which would have had pentagonal points. And instead it wound up being a greater stellated icosahedron, which works out fine, because now I have a lesser and a greater stellated icosahedron. But if I had beforehand known what I was folding, then I wouldn't have run into that issue. Quality over quantity, I had to do what I loved. I love origami. I think it's really cool. I think it's really interesting. It's kind of like a puzzle you put together yourself, especially this type of origami. And I really enjoyed it. I need to scale down the scope of what I was going to be working on. I initially intended, like I said, to do modular origami. I narrowed that down to polyhedra. I narrowed that down to these 2 polyhedra. And I'm glad I was able to do that, but I really should have done that earlier, because I would have had a better idea about what I was doing. Don't take on more than you can handle. So that's related to that point, which is that by taking on such a large task, I really couldn't have done all of polyhedra, because there are just too many, and you can come up with them. So that brings me to the next point, which is what is necessary to get your point across. I wanted to introduce these polyhedra, but I wanted to explore modular origami as a whole. And I think I got that across effectively, even though it wasn't all of modular origami, it was just these two specific polyhedrons. Next slide. So the results, I have 4 models. I have a greater stellated, I have a regular icosahedron, which is this one. It has 20 faces and 12 vertices. I have a regular dodecahedron. It's a frame, and it has pentagons inside it, which is really cool. It has 20 faces and 12 vertices. A lesser stellated icosahedron, which is this one, and a greater stellated icosahedron, which is this one. Slide. So I'd like to acknowledge my stepmother for giving me the idea to pursue this project. When I was younger, I used to do a lot more origami, and I kind of fell away from it for a while, but I wound up pursuing it again because she suggested to me, she said, you know, you used to do origami, why don't you get back into it? And I did, and I'm thankful for her to that. I wanted to also thank her for being patient with me for spending hours at a time just sitting there and folding. And I wanted to thank my advisor, Dave Lowe, for his assistance in judging my progress and for general capstone support. Next slide. These are my references. And thank you.